Welcome to the deep dive. We go deep, deep, deep into all sorts of things you might think you know.
Like what?
Well, today's a good example. We're talking about technetium.
Technetium?
Uh-huh. It doesn't exist naturally on Earth.
At least not in any kind of quantity you could actually use.
Right. We actually created ourselves as a byproduct of nuclear reactors.
Which is pretty wild.
It is wild. But here's the twist. It's also used in millions of medical scans every year.
Yeah, that's the crazy part. I mean, it really is a fascinating element. I mean, the fact that it was the very first element to be artificially created.
Oh, yeah, that's right.
It doesn't just exist in nuclear waste. We literally make it on purpose for medical imaging.
So in this deep dive, are we going to learn how an element went from being completely missing on Earth to being something we're both making by accident and making on purpose?
That's exactly what we're going to do.
That's wild. I love
It's
it.
a great story.
Where do we even begin with something like that?
Well, I think the best place to start is back in the 1870s
Okay.
with Dmitry Mendeleev.
Oh, yeah. The periodic table guy.
Exactly.
Mhm.
He's working on his periodic table, and he realizes there's this gap right below manganese.
Mhm.
And he thinks, based on the patterns he's seeing,
Right.
there should be an element there.
Yeah.
He even predicts what its properties should be.
Oh, wow.
And he calls this mystery element eka-manganese.
Wow. So he just knew it had to be there,
Yeah.
just based on how everything else lined up.
Pretty much, yeah. And, it was a revolutionary idea at the time, and it actually spurred this huge scientific treasure hunt.
Oh, really?
Oh, yeah.
Yeah.
Everybody wanted to be the one to find this missing element.
That makes sense. Did anybody get close?
Oh, there were some false starts. Like in the 1920s, there was this team of German scientists,
Okay.
and they thought they'd found it. They called it Masurium.
Masurium.
Yeah.
I think I've heard of that. Didn't it turn out to be the wrong thing?
It did. Later analysis showed that the methods they were using actually weren't sensitive enough to detect the tiny amounts of technetium that were probably in their samples.
Ah, so close.
So close.
So how did we go from, this theoretical element on the periodic table
Right.
to actually knowing it was real? Someone must have actually found it.
They did. In 1937, two Italian scientists, Carlo Perrier and Emilio Segre, they're working at the University of Palermo.
Okay.
And they were doing some experiments with a cyclotron.
The cyclotron. Oh, man. Physics class is coming back to me now. That's like a particle accelerator, right?
Yep. It accelerates charged particles
Right.
to extremely high speeds and then smashes them into a target.
Got it.
In this case, the target was molybdenum.
Molybdenum. Uh-huh.
And they bombarded it with these particles called deuterons, which are basically heavy hydrogen nuclei.
Okay, so they were basically trying to smash atoms together and see what happens.
Well, they were trying to transform molybdenum into something else,
Uh-huh.
and it worked.
They made technetium.
They did.
Wow.
They were the first ones to ever create technetium in a lab. It was a huge moment.
That must have been amazing for them.
I'm sure it was.
So they get to name it right.
Oh, yeah, they got naming rights. And they went with technetium
Technetium.
from the Greek word technetos, which means artificial.
Which makes sense, given the whole making it in a lab thing.
Right. Perfect name for the first ever artificially created element.
So we've got this lab-created element. But what is it actually like? What's it look like? What's it do?
It's a silvery gray metal.
Okay.
It usually comes in powder form,
Ah,
but there's a catch. It's radioactive.
right. Always important to remember that part.
Yeah, you don't want to be handling this stuff without taking precautions.
Definitely not. So I'm guessing we won't be seeing any technetium necklaces or anything like that anytime soon.
Probably not. But chemically speaking, it's really interesting.
Oh.
Oh, yeah. So on the periodic table, it sits right between manganese and rhenium.
Uh-huh.
And in terms of its behavior, it actually resembles rhenium more closely.
So it's kind of like a rebel in the family.
You could say that. It likes to do its own thing, especially when it comes to forming bonds. It really prefers to make covalent bonds, just like rhenium does.
Fascinating. I'm already getting the sense that this technetium is full of
That's
surprises.
because I have no idea. Just wait till we get to the part where this radioactive metal starts saving lives.
Wait. We're going from particle accelerators to medicine. Okay, I am definitely going to need to hear more about this.
Buckle up. It's going to be a wild ride.
Oh, I love it. All right, so radioactive metal saving lives. I got to know how that happens.
Well, it all starts with how technetium is made.
Okay.
Remember we were talking about nuclear reactors?
Yeah.
So when uranium or plutonium atoms split in a reactor,
Uh-huh.
it's called nuclear fission.
Right.
They form smaller atoms.
Okay.
And one of those byproducts is technetium-99.
Technetium-99. Okay. And that's the most common type of technetium.
Exactly. It's the most common isotope.
Isotope. Okay.
But there's a problem.
What's that?
Technetium-99, it has a really long half-life.
Oh, no.
Over 200,000 years.
200,000 years.
That means it stays radioactive for a very, very long time.
So it's basically nuclear waste.
Essentially, yes. And it's a big challenge because we have to figure out how to store it safely for, well, basically forever.
Yeah, that sounds tricky. So how do we go from this radioactive waste product
Right.
to something that's actually helpful in medicine?
Well, this is where it gets really interesting. See, there's another form of technetium-99
Oh.
called technetium-99 meter.
The M stands for what?
Metastable.
Metastable.
It means it's a slightly less stable form of technetium-99.
Okay, so technetium-99 meter is like the hyperactive little brother of technetium-99.
I like that analogy.
Huh.
And this little brother is actually the key to medical imaging.
Really?
It has a really short half-life, only 6 hours.
Okay, that's a lot better than 200,000 years.
Much better.
Haha. But why is that good for medical imaging?
Well, as it decays,
Uh-huh.
back to technetium-99,
Right.
it emits gamma rays.
Gamma rays. I know those can be dangerous, but they're also used in like X-rays and stuff, right?
Yeah. Exactly. So in controlled doses,
Right, man.
gamma rays can pass right through the body,
Uh-huh.
and we can detect them using special cameras.
And that lets doctors see what's going on inside without having to do surgery.
Exactly. We can create images of organs, tissues, all sorts of things.
So using the radioactivity of technetium-99 meters to see inside the body.
Precisely. It's like a little radioactive flashlight.
Wow. And since it has such a short half-life,
Yeah.
the patient's exposure to radiation is pretty minimal, right?
That's right. That's one of the big advantages of using technetium-99 meters. It decays quickly, so it doesn't stick around in the body for very long.
Okay, that makes sense. But how do they even get technetium-99 meters into the patient in the first place? Do they, like, eject it directly?
It's a little more complicated than that. They actually combine technetium-99 meters with special molecules
Okay.
that target certain organs or tissues.
Oh, so it's like a guided missile. It goes exactly where it needs to in the body.
Exactly. It's like attaching a GPS to the technetium-99 meters, telling it where to go.
I love it.
And then, yeah.
Once the technetium-99 meter reaches its destination, the gamma rays it emits can be picked up by a camera. And that's what creates the image.
So every year, millions of people are benefiting from this element
Right.
that started out as nuclear waste. It's kind of amazing. Science can turn problems into solutions like that.
I know. It's incredible.
But it also sounds really complicated. Like, where do hospitals even get technetium-99 meter? Do they have to, like, extract it from nuclear waste?
Well, it's mostly produced in a more controlled way, using something called a technetium-99 meter generator.
Generator.
Uh-huh.
Like a little power plant for technetium.
Not a power plant exactly, but it does produce technetium-99 meters on demand.
Okay, how does that work?
It uses molybdenum-99,
Molybdenum-99.
which is another byproduct of nuclear fission.
Oh, right.
And molybdenum-99 decays into technetium-99 meter.
Mm-hmm.
So the generator basically harnesses that natural decay process to create a fresh supply of technetium-99 meter whenever it's needed.
So they're not actually making technetium-99 meter. They're just, like, collecting it as the molybdenum-99 decays.
Exactly.
That's pretty clever.
And you want to hear something funny?
Always.
These generators are sometimes called technetium cows.
Technetium cows. I'm sorry, what?
No, it's a funny name, right?
I gotta hear about this. Why are they called cows?
Well, it has to do with how the technetium-99 meter is extracted from the generator.
Okay.
It kind of resembles milking a cow, but instead of milk, you get a saline solution, which is then used to separate out the technetium-99 meter.
So it's like a radioactive dairy farm. This is great.
It is kind of funny when you think about it that way.
Okay, but what about all that leftover technetium-99?
Right.
We talked about how it has that crazy long half-life.
Right.
What do they do with that?
Well, that's a major challenge.
Yeah.
I mean, technetium-99 meter has revolutionized medical imaging,
Mm-hmm.
but we still haven't quite figured out what to do with all that technetium-99 waste.
I can imagine. So what are scientists doing about it? The most common approach is deep geological disposal.
Deep geological disposal.
Basically burying it deep underground
Wait.
in very stable rock formations.
But wouldn't there be a risk of, like, leaks and stuff?
That's always a concern.
Yeah.
Groundwater contamination is a big worry.
Right.
It's a tricky issue, to be honest.
So are there any other options on the table?
Well, some researchers are looking into something called transmutation.
Transmutation. Is that like turning lead into gold, but with radioactive waste?
It's not quite alchemy,
Huh?
but it does involve transforming one element into another.
Okay.
And in the case of technetium-99, the idea is to bombard it with neutrons.
Back to the particle accelerator.
Well, the principle is similar.
Uh-huh.
The hope is that by bombarding technetium-99 with neutrons, we can transform it into technetium-100,
Technetium 100.
which has a super short half-life, only a matter of seconds,
Oh, wow.
and it decays very quickly into a stable form of ruthenium.
So they're basically zapping the dangerous stuff into something harmless.
That's the goal. It's still in the early stages of research, though. There are a lot of technical challenges to overcome.
Yeah, that makes sense. Okay, so we've talked about how we make technetium, how we use it in medicine, and even how we try to get rid of it. What else is there to say about this element?
Believe it or not, there's one more twist to this story, and it takes us beyond the confines of Earth.
Wait, hold on. What do you mean beyond Earth?
It turns out that technetium isn't just found here on Earth.
What? But I thought it was an artificial element. You know, something we created in a lab.
That's what makes this discovery so fascinating.
Okay, you've got me hooked. What is it?
We found technetium in stars.
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 Okay, technetium in stars. How is that even possible? Didn't we just spend the last hour talking about how it's artificial?
It is artificial here on Earth, but it turns out that out in space, in certain kinds of stars, technetium is actually pretty common.
So those stars are making it.
That's the amazing thing, yeah. We first found technetium in stars way back in the 1950s.
Wow, that was like the early days of, well, everything space-related. Sputnik hadn't even launched yet.
Exactly. It was an incredible discovery. This astronomer, Paul W. Merrill, he was looking at these stars called red giants.
Red giants, okay.
And he was using a technique called spectroscopy,
Spectroscopy.
which basically lets you analyze the light coming from a star
Right.
and figure out what it's made of.
Like a fingerprint for each element.
Exactly. And when he looked at the light from these red giants, bam, there was technetium.
Wow. So they're, what, like giant nuclear reactors in space cooking up technetium.
It's a great way to think about it. The process is called nucleosynthesis.
Nucleosynthesis.
And it all happens because of the incredible temperatures and pressures
Right.
at the cores of these stars.
So they're basically smashing atoms together like that cyclotron we talked about.
The principle is similar.
So they're making technetium by, what, smashing molybdenum with neutrons, like in that generator thing?
That's part of it. There's a process called neutron capture,
Neutron cap.
where a nucleus absorbs a neutron,
Okay.
which makes it a heavier isotope of the same element.
Right, right. But how does that turn molybdenum into technetium?
Well, if a nucleus keeps absorbing neutrons,
Uh-huh.
it eventually becomes unstable,
Okay.
and it decays into a different element.
So that's how technetium is born in stars?
Exactly. It's part of a process called the CES process,
The CES process.
which is how lots of heavy elements are made in stars.
This is blowing my mind. So technetium, this thing we make in labs, this thing we use to see inside the human body, it's actually being created out in space, in the hearts of dying stars.
I know. It's pretty incredible, right?
It really makes you feel connected to, like, the entire universe. It's not just something in a textbook. It's actually happening out there.
I love that. And that's what's so cool about technetium. It takes us on this journey
Uh-huh.
from a missing element on the periodic table
Right.
to a lab creation,
Yeah.
to a medical marvel.
And now it's a cosmic wonder, too. This deep dive has been awesome. I feel like I've learned so much about this element that I honestly had never even thought about before.
I'm glad to hear that.
So what's the big takeaway here?
I think it's that science is full of surprises. We think we know something, and then bam, a new discovery comes along and completely changes our understanding.
Totally. And technetium's story is a perfect example of that. We're still learning about this element, and who knows what other amazing things we'll discover about it in the future.
Exactly. The journey of scientific exploration never ends.
Well said. Well, I think that about wraps it up for our deep dive into the world of technetium. It's been a wild ride.
It has.
From the periodic table to nuclear reactors to medical breakthroughs and the CES process in stars. Who knew one element could have such an incredible story?
It just goes to show there's always more to learn.
Absolutely. Big thanks to our expert for guiding us through this amazing deep dive.
It was my pleasure. Always happy to talk about technetium.
And to all our listeners out there, thanks for joining us on the deep dive. We'll see you next time for another adventure into the unknown.